I wanted to record just a couple of examples here because there is a very important topic that was glossed over on your videos 6162, and that is a question like this. So you do have one of these on your homework, so let's take a look at how I might go about it, and then let's take a look at how that relates to Theorem 6.1, which is the exponential growth and decay model. So I'm starting with dy over dx equals 2/3 y. And again, if they give it to you as y prime equals 2/3 y, it's best to replace y prime with dy over dx, just so you understand exactly what's happening and that you're separating the y's with the x's. So what I would do first here is I would multiply each side by dx, which would give me dy equals 2/3 y dx. Now obviously this is not okay. I can't integrate y with respect to x, so I'm going to divide each side by y, giving me dy over y equals 2/3 dx. Well, dy over y gives me natural log of y, because remember this is like u prime over u, and when we integrate, oh, I did not write my integration symbols. Someone slapped my hand. So I have natural log of y, and then if I integrate 2/3 dx, remember I could just keep the 2/3 on the outside. Let's just do that real quick. 2/3, and then I'm just integrating dx. So what's going to happen? Well, I've got my 2/3. If I integrate dx, I get x, and then plus c. Now, this was talked about in your videos, but keep in mind there is a plus c here, and then there's a different plus c here, so c1, c2, and you might see that notation in your book. So just keep in mind that what's going to happen is I'm going to subtract this c and subtract it from this c, and that gives me a totally different c, but it's still just a c. It's some constant that we don't know the value of. So where we stand right now is natural log of y equals 2/3 x plus c. So from here, obviously, I want y equals, not natural log of y equals, so I'm going to exponentiate. I'm going to take e to the natural log of y equals e to the 2/3 x plus c. Pay attention to this part. We know that e natural log of y, those things are inverses, so I just get y. That's not an issue. This is where this little math magic part comes in. I've got e to the 2/3 x plus c. This is all an exponent. So I'm going to use my properties of exponents to call that e to the c times e to the 2/3 x. Now, e to the c is just some other constant, and that's the tricky part, and that's the part that was glossed over that's so important, because this can now be rewritten as y equals, remember this is just some other constant, so it's just another c value, and I'm not using subscripts, but it's just some c value, e to the 2/3 x, or if you would rather, 2x over 3. That would be my solution, my general solution. Now let's talk about Theorem 6.1. So in Theorem 6.1, we're told, hey, if you ever have something that looks like this, that is proportional, then you can just magically use this. Well, where did that come from? I bet you can guess it has something to do with this example we just talked about. So if I look at dy over dt equals ky, again, I'm going to end up with dy over y equals k dt. And if I integrate both of these, I'm going to end up with natural log of y equals k is just some constant on the outside. And if I integrate dt, I get t plus c. And again, I'm not going to write the plus c on the left side because I'm just going to end up subtracting it anyway. So now if I take e to the natural log of y equals e to the kt plus c, that gives me y equals, and then over here I'm going to do the exact same thing I did before. E to the c times e to the kt. Well, e to the c is just some other c value, so that's c e to the kt. So when you get a theorem like this, don't just say, okay, let's use it. Say, where did that come from? Because that is where it came from. Notice those match up. Now, you don't have to ever do this work for the exponential growth and decay questions, but it's important that you understand that all we did is the same work that we know how to do for a question like this to come up with what will always be the general solution. The other topic that hasn't really been touched on was interest, and there are different kinds of interest. We're talking about interest that is compounded, so not simple interest, but compounded, where they take the amount of money that you're earning on interest and they roll it back into the principal, and so you're actually earning interest on interest, which is fantastic, unless you're borrowing money, and then in which case compounded is not fantastic. But let's say I am in a situation where I am going to need $500,000 by the end of 20 years. And I'm earning a rate of, 30 years. And I'm earning a rate of 5%. Again, this doesn't really have anything to do with calculus. We're really just going to be plugging in the 500,000. I'm solving for P because the question is, how much do I have to invest in order to have $500,000 at the end of 30 years? I would take 1 plus 5% is 0.05. Because this is going to be, n is going to be compounded daily. So n is the number of times it's compounded per year. So if it's daily, we do 365. Yes, technically you could do 365.25, but we're going to go with 365. And then 365 up here times 30 years. So again, not a whole lot of calculus going on here. We're just going to do the algebra. So the trick here is to not show too much work because you're going to do all of this work in your calculator. So I'm going to do all of this in my calculator, and I'm not going to show any work in between. That gives me 4.4812287. Now notice I went crazy with my decimals, but that's the whole point, is we don't want to get mixed up and round too often in the middle of a question. So now I'm going to take each side divided by the 4.4812287, and what I end up with is 111,576.54. Now notice I'm rounding here. Why am I rounding? Because I'm finding the principal amount. So essentially what it's saying is if I need 500,000 in 30 years at 5%, compounded daily, n times per year daily, I'm going to have to invest $111,000, $111,576.54 in order for that to work. So just keep in mind that daily would be 365. This would be monthly, and if it's every other month, it's 6 times. You get the idea. Usually it's daily or monthly. Now, if we're compounded continuously, again, this equation comes from calculus, and I'm not going to take you through that, but essentially we're finding a limit. The limit of this actually ends up being e, which is pretty cool. So I think I took you through that in Calculus 1, but if I didn't, you can Google where this formula came from. But again, you're going to get similar types of questions here, but quite often you'll be asked to solve for r or to solve for t. So I might say, hey, I'm going to have $50,000, and I'm starting with, say, $100,000. And I have a rate of, say, 6%, and I'm saying how much time, if it's compounded continuously, how much time. In fact, let's go ahead and make this 5% just for fun so that we can compare what the difference is. But I'm starting at $100,000, so again, just doing algebra, I would take each side divided by 100,000, so that would give me 5 equals e 0.05t. And again, hopefully we know how to solve for this. If I have an e, I'm going to take the natural log of each side. And again, I'm hoping this is all review for you. these two cancel out, so I have the natural log of 5 equals 0.05t, which means t is the natural log of 5 divided by 0.05. So if I take the natural log of 5 and divide it by 0.05, I get 32.1888. So about 32 years is how long, which is very similar to what we found here. Obviously, I'm investing less, so I have to invest it a little bit longer. But again, that's just a quick review as to how you find interest compounded continuously or yearly, monthly, daily, etc.